just visited my
Recording
youngest son
is on.
Okay.
over in Waterloo. So
Yeah,
there you go.
they just released them from the loony bin.
Milton Correctional Institute. I'll fess up.
Did you take your medication, Eric?
The 5-prong device that it's not enough. It's not working.
Hey, Dad, how's it going? Don't forget, put me in the will and get rid of Eric. He's not a good son.
Yeah. Nice try. I take him out to dinner. When's the last time you took him out to dinner, huh?
Kiss ass.
All right. All right. I'm going to go into mute mode. You don't want to listen to all my jazz here. So.
No, not really. Okay, I guess we might as well get started. Good evening, everybody. Just got all the usual face here. I think, Andrew, this is your first time to one of our PARC homebrew meetings, I think, isn't it?
It is, yeah.
Andrew's VA3 IEG is one of our Kingston hams. Well, Bath to be exact, I guess. So welcome for coming out, Andrew. And
thank you.
So tonight we have a couple things here. Kevin is going to do another segment of his cool chips, and then Dave has part one of my journey down the rabbit hole. So I guess, Kevin, if you want to get started, and I know I alluded to something on the on Groups.io earlier. Maybe we should do a recap at some point of just a brief of at one point of the different chips that you've presented, if you still have records of it.
Oh, I do. Otherwise, I lose track. So it's all written down somewhere.
I was almost thinking, now what can we build out of these chips? I know maybe one or two of those chips might be a little bit out there, but anyway, food for thought.
Yeah, some are exotic, some not. We'll see what you think of this one, or the ones tonight. But and I don't really know that much about them. I didn't spend a lot of time digging into the chip. It just looked like, oh, that's an interesting specification. I wondered what you could do with that. So anyway,
let's find out.
Yeah. Share video. No, I don't want to. Oh, geez. Share screen. Okay, there. No. Obviously, screen share. Obviously, it's been a while since I've done one because I have to look and see.
For more, if you can't remember how to.
Yeah, where the hell to share the screen? So anyway, begin. Okay, everybody see that?
Yep.
Okay. I don't know if anybody's done any rapid tests, but I saw this cartoon on XKCD, and I thought, oh, that's appropriate.
Yes.
If you've done any of these, I like the one where it's got one, click to expand the menu, right? Anyway, a little bit of levity. So,
use it.
What I found, or what I was looking through, and I don't know what, some rabbit, like Dave says, some rabbit hole. But I found they make these chips that do beam forming, right? And you go, well, what the heck is beam forming, right? So, and it's not as uncommon as you might think, but so they use a bunch of static antennas, and they're usually higher frequency, right? So in this case, they show a little chip here, sort of a simplified representation with patch antennas. And by delaying the phase and the amplitude and that sort of thing to each of the antennas, you can control and steer the lobe of the beam, right? So that sounds pretty cool. And this was sort of, I put this one in for you, Dave. It's a mathematical representation. So you probably understand it. I know I don't really, but it's like a bunch of, basically it's a linear array. And what they're saying is, if you want to steer the beam, you just set a predictable delay between each one. And it's based on the angle that you want and the distance between the antennas and blah, blah, blah. And then you end up with all these time delays essentially. And by doing that, you can steer this array, whichever direction you want. And then I was thinking, oh, that's what led me to this thing. I thought, because of the Starlink, like the SpaceX antennas, the Starlink ground terminals used a phased array to follow the satellites. And I found some guy that did a teardown on one. I mean, this is sort of the whole dish. It's like, I don't know, about a couple feet in diameter. There you can see his thumb there on the edge. And I just zoomed in on one corner, and you can see all the individual little patch antennas that they use to do this thing. And this This guy's on teslanorth.com. He's got a bunch of stuff on there, but he goes into great detail on this thing. He pulls this cover off, and you can even see in the center, they've got the clock circuit. It's right in the center, so that they have predictable time delays in like circular arrangements around the center. It's quite detailed. Anyway, and it's used everywhere, like ultrasound. Your Wi-Fi routers, the ones that look like upside down spiders, you know, they're using beamforming. 5G mobile is going to be a big one. Radar, military radar, satellite comm links, blah blah blah. So, you know, that's going to 5G apparently is the next big thing with all this beamforming stuff, so they can actually direct the antennas to point directly to your phone when they're talking to it. Otherwise, they're going to need even more antennas everywhere. So I found a couple of chips that do this. This is all done on the chip level now. And this was one that I thought was kind of interesting. It's like multi-level, 16 channels, transmit receive switches, amplifiers, all this kind of stuff. But the interest, and it's meant for ultrasound. So medical ultrasound is the application. But crap. But the bandwidth is interesting. It goes up to 20 megahertz. Wouldn't that be neat if you could do something like this in HF? I mean, it's got the bandwidth. You could theoretically do beamforming with this chip on like 20 meters. I think. I don't know. That's what struck me as kind of odd. And it's got like a CW mode and all this kind of stuff. And this thing switches like 100 volts. It's not a trivial amount of power that it can switch. So anyway, that was one thing. And then there's even a fancier version here that this is one meant for the 5G towers at 24 gigahertz. So it's like 8 channels, transmit, receive, mixers, all this kind of stuff built on one chip. It's like, so it's a fairly comprehensive chip, but it only goes to like 15 dBm. So you obviously need amplifiers and stuff with it. But so anyway, that's, you know, these things are getting quite sophisticated. So anyway, that was it. I couldn't find any prices on these things, so I'm not sure how much they are. I suspect they're not cheap, but anyway, another project in case anybody's interested.
Well, I did make a note there of that chip, and my first question up was going to be how much was that chip, but you probably answered it, because if you have to ask it, you can't afford it, right? Kind of thing.
Or
advertising it.
Yeah, I mean, they don't. You know, it's not like you can go buy 100 of them at Moser or something like that. At least I didn't find them anyway. But
so make sure I understand then. So all those little individual antennas, then they delay the propagation.
You delay. You either change the amplitude, or you delay the signal between them, and by doing that, then you can do this with the lobe. I mean, that's what the Starlink and ground terminals do, right? The satellites are whipping overhead all the time, and they know where the satellites are, so it just it receives on a particular angle and follows the satellite across, and then the next one comes, and the next one comes. That's why they need so many, right? Because it's always following some satellite that's in view.
So you're actually turning your antenna without any moving parts then.
Right. It's a electrically rotatable antenna. So if you had half a dozen vertical 20-meter dipoles, say, for instance, if you could hook it up to that multi-channel chip, you could steer the beam anywhere you want, sort of thing.
Well, maybe we should have our 2 or 3 days at Eric and put this together up there. Hassan, you have a comment?
Yeah, actually 2 comments. Just on the last point, if one way to imagine it is imagine you've got a compass needle and you've got 2 magnets. So if you have one magnet and you rotate it, you pull the compass needle towards it. On the other hand, if you had 2 magnets, one north, one east, and you vary the strength, you could also rotate it that way. I've never tried this, but I take it on faith that it's possible. But just by the amplitude of 2 coils, you could rotate the needle to any position.
Actually, they do that in all the industrial drives now, Hassan. They control, by controlling the reactive current and the torque current, they can set the magnetic field wherever they want. So it does actually work. I see it every day when I turn drives on. So yes,
Perfect.
it does.
Awesome.
It does actually work.
Yeah. Yeah, with 3-phase, you get a smoothly rotating field, but in theory, you could do it with 2 coils only.
Yeah.
That's the
So,
experiment that you
but
did
what,
in
but
your basement has said.
yeah, well, I had another comment though about that TI chip, the one with the ultrasound.
Yeah.
I was just thinking the chart you put on there said the delay equals D over C cos theta.
Yeah.
So C in this case has to be the speed of light for RF, but for ultrasound it's going to be like 1,000,000 times slower, or 100,000 times slower. So that's the flaw in the ointment. Like,
Well, I did have the looking at the data sheet, the minimum delay resolution is 5 nanoseconds. So that's pretty sporty, I think.
But the distance between, okay, so that 5
Five
nanoseconds,
nanoseconds is,
5 feet.
Yeah, that's 5 feet.
That might actually work then. But the problem is how much jitter will there be? It's got to be the precision is the other factor. So if it's not precise, it'll just screw up it'll
CW
wobble.
mode jitter is 100 femtoseconds. I don't have to do the math to think that that's fairly good.
Okay, your next argument, Hassan?
Yeah. Is what? What was that?
Well, your next argument.
Okay, my next, well, no, my next argument is I'm wondering if that 20 megahertz is total bandwidth or
See,
per channel.
I don't know. It takes, you'd have to dive into it a bit deeper than what I did. I just picked out a few numbers and I thought, oh, that's interesting. I wonder if there's anything worth doing there. I mean, you need something to drive this thing as well. You need something to set up the angles that you want and the delays. So there has to be a bunch of math behind all this.
Well, one problem at a time. If it's a $5 chip, buy a couple and then just play with it and figure it out later.
Well, and it's got an SPI or I2C interface, one of those, something like that. So you can, and it can store, I think, configuration. So you can kind of say, go to this angle, boom, and it's already stored, and you pre-store it, and away it goes.
Yeah. So the traditional way to produce delays for phased array antennas is just variable lengths of coax. Like just use longer coax, you get a different delay.
Yeah, but where's the fun in that?
Yeah.
We can make it so complicated.
Yeah,
That's right.
we might have to use the blue pill on this one instead of an Arduino.
Yeah, I think so.
Dave, you had a comment?
Yeah, this reminds me of that very large array. I think it's in Arizona, where they got the miles of dishes.
That's
lined
Australia, isn't it?
Yeah, and it's the same principle, except they're a receiving, and they've got it spaced in certain increments of wavelength, and they can add it together, and they can superimpose it, and they can get a much stronger signal just by doing that. So it's a similar kind of.
Yeah, exactly. No, that's exactly what this is. Yeah.
Except this is transmitting, and you're steering it, right? Which is cool because Kevin, you hit the nail on the head there in terms of like Starlink. This would be perfect if you could get the frequency for like tracking a satellite, doing satellite communications, right?
Yeah. Yeah, you could.
Well, somebody could.
Somebody could.
Let me see.
Yeah, you could just put in those numbers for tracking and just like
the first one there.
Yeah.
Sam.
Yeah. Anyway, so that's something else to think about. Different rabbit hole.
All right. Well, thanks, Kevin. Is there any other comments for Kevin? Questions? Okay. Well, next up we have Dave V3OOI with his journey down the rabbit hole, part 1. It seems like we didn't hear much from Dave over the winter or fall and whatnot. Now I get to know why. You got a ton of rabbit hole, a deep rabbit hole, Dave, do you?
No, it's because of work, man. Because as of December, I was working at Scarborough Hospital, and I was working like I mean, like 10 hours a day, like 10 hours a day, like your head's down and you couldn't do anything else. End of the day, I'm just totally wiped. So no, last year I just didn't do very much. Like I did, whatever I could.
Yeah.
And so now that that's done, I was able to start looking at things. But last year, let me how do I share my screen here? Share screen, there it is. Okay, you guys should see my screen now, right? Can you guys see my screen?
Yep.
Yep.
Okay, so last year, this is I thought I would document how I think. It's kind of scary, but it's like how I go through the process of doing things. And so like I go down one rabbit hole and leads to another rabbit hole. And I thought I'd just share with you a journey I went on since last year and why I ended up where I did. So basically I'm going to quote Charlie Morris here is that this is not a tutorial, it's a log. Okay, my background is not engineering. It's I was trained as an experimental physicist way back, and so I know or I understand how to do experiments, and that's how I learn, is by doing experiments. And that's why I love LT Spice so much, is that I can go and I can experiment and I can test things and I can prove or disprove what's going on and I figure things out. So basically how this journey started, and I talked a little bit about this last week as a teaser, but last year I purchased an Ender 3D printer, and Eric and I got together, set it up, and as I bought the cheaper unit, and I found out there's a whole bunch of mods for it. So as I was looking for mods, there's a laser module you can buy, and you could strap onto it. And then as I was looking at this laser module, I stumbled across some people that were using them to etch PCB boards. And I thought, oh, that is cool. How did these laser modules work? Nudge, nudge, wink, wink, first rabbit hole. So I started looking at this, and they use laser diodes here. And these laser diodes are typically low voltage, but higher current. And these modules, they use pulse width modulation to control the voltage. And so a lot of them, they use a buck converter to step down the voltage. So they take like a 12 volt feed, because most of these things, I think it's these extruders are run on 12 volts. Dwayne probably knows a lot more than me, but they run in a higher voltage and they have to be stepped down via this buck converter to power the laser diode. And you can control the laser power by varying the pulse width modulation of the diode. So this is a map of the rabbit holes I went down. So I first started looking at laser modules, and then they use buck converters. And I thought, hey, you know what? I've seen these buck converters all over the place. How do they work? So I tried, creating experiments, modeling it, and I couldn't get the damn thing to work. So that led me to go down the first rabbit hole of inductors, because these things are based on a inductor, and it's some of the things they were saying. It's something we all know. We hear, oh, an inductor is used to delay the current. It delays the phase, and it opposes changes in current, and it does anything it can to keep the voltage the same, and blah blah blah. And I was looking at that and going, what the heck does that mean? How does it do that? So rabbit hole number one. So the buck converter relies on a MOSFET. I couldn't make it work, so I had to go and figure out, okay, why can't this thing work with the MOSFETs I put in? So rabbit hole number 2, and that had to do with a lot of the capacitance that are associated with MOSFETs. So once I, learned a little bit more about MOSFETs, Peter, what was this, 3 years ago, 2 years ago? We were
Yeah, it was a year before COVID.
Yeah, we were working on this transceiver called the Dueling 612s, and it was based on 2 SA612s mixers with a crystal filter amp in between, and it came out of a design by Pete Giuliano. And so we built this thing, and it worked. I was able to make contacts, but then I found out it was very, very dirty. The power amp is extremely dirty. So then I started revisiting the power amp of that design. And as I was doing that, that led me down 2 additional rabbit holes where, to look at the purity of the power amp, I had to do an FFT and LT spice. And I thought I knew how to do a FFT and LT spice, but I didn't know jack. It's fairly complex. So I had to go back to first principles for FFT and refresh my memory about how it works. And the other powerful piece that came out of this was using LT spice measurements to automate your measurements. Because going and running a simulation and going and measuring the peak-to-peak voltage for each amp, it's nonsense. So there are ways that you could automate your measurements, and you could run formulas, and you could do all kinds of things. So I was able to go and use that to characterize various power amps. So this is so when I looked at the buck converter, okay, the way it works, and you guys may already know this, and if you do, watch Netflix or something, but basically what it is, it's got a diode, and it only allows current to flow in one direction. It's got an inductor, and it's got a capacitor which charges, and then you've got your load. Okay, so the way it works, when it's open, there's nothing flowing. So you close it, current starts to flow. So, and I'm assuming current's going from minus to plus, from a low voltage to a higher voltage. So it's flowing this way, and it goes across the inductor, charges the capacitor, and makes it through the load. And everything you read says, oh, the inductor opposes the current, and so therefore it builds up a more positive charge on this side and a more negative charge on that side. And like, I'm scratching my head going, how the hell does it do that? So then when the switch is open, so now current stops flowing this way, and so now the diode, current flows through the diode, the inductor becomes a battery, minus to plus, current flows this way, and it's dumped into the load, and the capacitor also discharges as well. And you can see this here. So the blue line is when the switch is, when it's at 1. When the blue line here is at 1, the switch is closed. So here you can see the current coming up, and it's raising up through the inductor. The inductor is opposing it. Then when it reaches full charge, the switch is opened, and it starts discharging. And you repeat this over and over again, and you get a net current or a net voltage coming out. So the way I arrived at that was that I stumbled across this guy on the YouTube. He's a professor at this university here, out of Arizona State or something like that. And so he had a lecture where he talks about these buck converters, and he does a design, and he says, okay, this is the parameters I want. I want 36 volts in, I want 12 volts out. That's my switching frequency, that's my load, blah, blah, blah. That's how much ripple I want. And here's the equations, and here's what I'm going to come up with. So this design here, with these values, which I use, by the way, is going to produce 12 volts output, and it's going to produce 10 amps output. So I thought, okay, great. Let me simulate that in LT Spice. Now, I'll spoiler alert. I tried doing it with a MOSFET, and it didn't work. So what I did, I said, okay, well, let me check, see if it's the MOSFET. Again, I did an experiment. So I said, let me replace the MOSFET and let me put a voltage control switch in, and let me see if I can get it to work. Because if this works with a voltage control switch, then I know it's a MOSFET problem. So I designed this experiment to go and test it out. And sure enough, it works. And it works perfectly. So I've got 2 plot planes here. And by the way, if you want to know how to do the 2 plot planes in LT Spice, you right-click on the plot area and you select add a plot plane, and a second plot plane will come up, and you can put different plots in there for the same simulation. So here you're seeing the voltage in green at V out, and you can see the voltage is around 12 volts. It's got a little bit of ripple. So sure enough, I'm getting about 12 volts out. And the bluish line here, that's the current flowing through the load. And sure enough, I'm getting roughly around 10 amps coming out. And the red here is the switching frequency. That's just the this switch being open and closed. Okay, now the bottom plot is showing the voltage across the inductor. So I'm trying to understand why they say it's more positive on one side or more negative on the other side. So I thought, okay, let me see if this is what's happening in real life. So by the way, if you want to know how to use the switch, the voltage control switch, if you go to this wiki page, it's got all the details of how to use a switch, how to set up a switch, a voltage control switch. So if you look at when the switch is off, okay, so the switch is off here. So green, I messed up this, the colors here. Red should have been the switch, but red is actually the voltage output. So it's V out, the voltage here, minus the voltage here. So it's the voltage difference across here. Okay, so red is actually the voltage difference across the inductor, and the green is the switching, is the switch being open and closed. So with the switch closed, with it 0, you see you get 12 volts. You get, it's more positive on this, on V outside, right? So it's a positive voltage. But when the switch comes on, is that right? Do I have it backwards? No, I've got it backwards. When the switch is closed, when the switch is open, the voltage goes negative. No, that's right. That's right. Sorry, I'm confusing myself. So when the switch is now open or closed, so you get a really negative voltage. So VI is bigger than V out. So the voltage is in fact building up here. You're getting a bigger voltage when this switch is closed because the inductor is opposing the current going through it. So you're going to get a higher voltage here than here. So sure enough, you're getting a negative voltage when the switch is closed, and you're getting a positive voltage when the switch is open, and the inductor is in fact acting as a battery. So we have a happy cat. This appears to be working. I still don't understand why it's going positive and negative, but that'll come in due time.
Dave?
Yep.
Do you mean due time in a couple of slides or in due time down the road?
Couple of slides.
Okay. Okay.
So here now is I put a IRF 510 and I put the a voltage to it, to the gate, to turn it on and off, and I got 104 millivolts out. Like, not a happy cat. So it's like, what the heck am I doing wrong here? So this started the journey down the rabbit holes. So after I went and I investigated MOSFETs, it's a dope moment here. and you'll see later on, is that these MOSFETs have a VGS. In order for them to turn on, the gate voltage must be higher than the source voltage by a certain amount. And I think for the IRF 510, it's 3 or 4 volts. It's of that order. Okay, so I was putting 5 volts in because I'm used to the what's this, the source being grounded. So if it's at 0 volts, right, then 5 volts would surely turn it on. But in this case, it's not 0 volts. It's some voltage that's going across. So that's why this didn't work. So anyway, that leads now into the first rabbit hole of what an inductor is doing. Any questions so far? So what I'm going to do is I'm going to talk a little bit about magnetic field. There's no equations. There's no math. This is all pictorial stuff, LT Spice stuff I'm doing. So first of all, I'm going to just talk about, oh, by the way, yeah, and you know, you guys, I'm sure many of you already know this. You know, you may have forgotten it, may have misunderstood it. Some of you may not know this, but this was a refresher to me because I studied physics like 30 years ago, and I had to go back to like, what's Faraday's law? What's Lenz's law? What does it mean? And so, so I'll go through some of this stuff purely from a hand-waving, high-level perspective, just to explain what an inductor is doing. So we start off our journey by, you know, you've got a piece of wire, and you've got a magnetic field around it. I'm sure in your grade school math, you took iron filings and you put it around a wire, and you got the iron filings to go around in circle, right? So that's a standard science experiment I think we all have done. And there's a magnetic field going around the wire. And that's what the right-hand rule is for. You point your thumb in the direction of current, and your fingers curl in the direction of the magnetic flux. So now if you take that straight wire and you bend it on itself, well, those concentric circles also bend. And if you keep bending it, the concentric circles keep bending, and eventually you end up with a magnetic field like a bar magnet. So then your coil, that's how you get a magnetic field going through your coil. It's just by adding up all these flux lines going around that's perpendicular to the flow of current. It's coming around, and it's still perpendicular to the flow of current. But the flow of current now is going around a circle, so you get a whole bunch of these lines, and it becomes like a toroid. Here you're looking down the center, and so it becomes like a toroid. Okay, makes sense, right? So now, with that same coil, we now go to Faraday's law. And Faraday's law says that if you've got a piece of wire, a coil of wire, a length of wire, and that wire has a changing magnetic field. So the changing magnetic flux across that wire, it induces a voltage and a current in that coil. If the coil is terminated, you've got some kind of a load, you'll get a current. If it's not terminated, you just get an EMF, you just get a voltage across the points. So if you're a bug and you're sitting on this wire and someone is moving this magnet towards you, you're going to be seeing these lines changing, because each one of these lines is a flux line, and you're seeing a changing magnetic field. So that changing magnetic field is inducing a voltage and a current in that coil. And that should come as no surprise, because that's how a generator works, right? You've got 2 magnets, and you've got some wire, and you spin it around, and it generates a current in that wire. And you're taking mechanical work, and you're converting mechanical work into electrical energy. And Einstein and the boys are happy. You're not violating any laws in thermodynamics. So, and here's a little video of showing that as this is moving, you'll see the coil of wire seeing different magnetic field lines crossing it. So as it's going, as these magnetic field lines are crossing the wires, it's inducing a voltage and a current in this coil of wire. If the coil is terminated, it's going to induce a current. Obviously, no current can flow if there's not a return path. Makes sense, right? Pretty straightforward stuff. No rocket science there. So this is the rock. Now we get to something a little bit more meat. So if you've got a coil and you've got a battery and you've got a switch, okay? If the switch is open, okay, there's no current flowing through this coil. So the current going through it is 0. When you close that switch, the current is going to go to, say, 1 amp. So because the current is going from 0 to 1 amp, the magnetic field in this coil is changing. The magnetic field has to change. Forget about imposing or any of that stuff. It's the current has to ramp up through the coil, and as it's ramping up, the coil, the magnetic field is growing. Now, as that magnetic field is growing, it's going to induce a voltage and a current in itself. So here, let me just show you the animation here. So you can see the currents flowing through, and you can see the field building up. The field's building, 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 building. Now, as the field is building, those magnetic field lines are changing, and it's inducing a voltage and a current in this coil. Now, the thing to think about, okay, is which direction is that current going to flow in? And if you think about it, okay, the current, let's say the current is flowing this way. Okay, if it induces a voltage and a current, and the current is in the same direction as the original current, then you would get an increase in current, then you'd get an increase in field, you get another increase in current, you get another increase in field, and this thing would just go atomic. It would probably just explode. You're violating the laws of physics here. You're creating a perpetual motion machine. So the current has to oppose the field. It has to oppose it. It can't enhance the field because this thing would just run away. It's like a positive feedback loop, and it would just keep growing and growing and growing, and eventually the coil would melt, or you get so much current going through this coil it would blow up, or something nasty would happen. So what Lenz's law is saying that induction, when you induce that current and that voltage, it opposes the original current. So that's where that comes from. That you hear that a inductor imposes a current going through it. It's because of the field is growing. It's inducing, using Faraday's law, it's inducing another current, and that current, it's based on Lenz's law. It's impeding, it's opposing the original current. So in the case of decreasing, same thing applies. So, but in this case, the field now is shrinking, it's decreasing, the field is changing. Since the field is changing, it's going to induce a current, and it's going to induce a voltage in this coil. So here we turn off the switch. And so in this case, the current's going from, say, 1 amp to 0. The current has to decrease. So that decrease in current causes the field to decrease. And you can see here the field decreasing. And as that field is decreasing, it's inducing, by Faraday's law, it's inducing a current and a voltage in this coil. Now in this case, since the current is going in this direction, but the current is decreasing, the current, you could think of the current as negative. Okay, it's not really negative, but it's a negative decrease. So it's got to impose that, so the current is going to flow in the direction of this current. And that's why you hear that an inductor does whatever it can to keep the current the same. That's why. Okay, so in the two cases you've got, I've just got a couple more slides and I'm done. So in the case where the current is increasing, you're going from 0 to 1 amp, the field starts to increase by Faraday's law. You're inducing a current and a voltage and a current in that coil. That current has to oppose this current. Because if it didn't, and it went in the same direction, then you'd have an increase in current, you'd have a bigger field, then you'd have more current, and it would just be a feedback loop, right? Same thing with the decreasing. So in this case, the current is decreasing. You've turned off the current. The current is decreasing. So now the current here, the decreasing field is going to generate a voltage and a current, which is going to oppose the change in current. So it's going to now produce a current in this direction, and that's why you need to have like I can't remember if it's called a snubber or a flyback diode, or there's some term for it where you got to put a diode across a relay coil. That's why, because that coil has got a magnetic field. When you turn it off, that shrinking field generates more current, and that current has to go somewhere. So you put a diode across here to get that current to short out. Okay, and we could demonstrate this in LT Spice quite easily. So I've got a little circuit here in LT Spice. So I've got an impulse function, and I set it to rise time of 1 nanosecond. It's 10 volts. It lasts for 100 microseconds, and then it drops, and 300 microseconds later, it repeats. So I put a small resistor here so I could actually measure a voltage here. I wanted to have a voltage drop across this resistor, and then I've got the honker of a inductor here so I could see the charge and discharge. So in the first case here now, the voltage is the pulse is turning on. So here it's like the switch turning on in your converter, in your buck converter. So you could see the voltage at 0, and all of a sudden the voltage goes right up to 10 volts. Then it's slowly coming down, okay? Because initially the inductor, through Faraday's law and Lenz's law, it's going to impose that current coming through it, and so the voltage slowly decreases down to 0. Steady state, there's no current flowing across here, or there is a small amount of current, and that's because of the windings, the resistance of the windings, right? There'll be a small voltage drop across here because of the resistance in the windings. There'll be a steady current flowing through it. Once you've got a steady current flowing through the inductor, the magnetic field is not changing. It's rigid, it's there, it's not changing, so you're not inducing any fields. So you could see that here, and the interesting, and so let me not talk about that just yet. So in the case of the it turning off, so in this case now I'm turning off the voltage. So all of a sudden now the voltage is turned off at this point. Okay, so there's no voltage here coming off. This is 0 here now, or it's open circuit. And so you see all of a sudden the inductor, the voltage across the inductor goes to minus 10 volts, right? The inductor has a whole bunch of charge. That magnetic field has to collapse, and that energy in the magnetic field has to go somewhere. And so then you see the current slowly decreasing through it. Now, the interesting thing is, if you look at this inductor, for it to charge and discharge, here's the time. So I just took the time here for it to go from 10 volts to, I just picked 1 volt. And here it took 23 microseconds for it to go from 10 volts to 1 volt. And for it to go from minus 10 volts to minus 1 volts, it takes it 14 microseconds. So the time it takes for it to discharge is, like half the time of it for it to charge, which makes sense because you couldn't have, in this specific configuration, you couldn't have the inductor taking a longer time to discharge, because then you'd be violating, laws of thermodynamics. You could create a perpetual motion machine. It's got to discharge faster. It's got to do with the having a reversible process, right? Something to do with having a reversible process. The process can't be 100%. You got to have losses. So that's why we get a positive and negative across the inductor when this is closed. And when it's open, that's why we get a negative. The polarity switches around. Not the polarity, but the voltage difference across the inductor is greater on this side when the switch is open, and when the switch is closed, the voltage is higher in this side and lower in this side. So that's it. So the next rabbit hole will be MOSFETs, and I'll save that for another time.
Okay, thank you, Dave. I don't see any questions so far, but I got a couple of comments. What would have been interesting on your slide 17? It would have been interesting if you stuck a diode, the counter EMF diode, on that slide, just to see,
Sure.
We all know what happens, but it still would have been nice to see it on how LT Spice handled the shorting out of that counter EMF.
Yeah, and actually, Peter, what would be really interesting is to tune it to try and see if you could put a resistor there and a diode, and you can get it to slow down the discharge rate.
Well, that's the nice thing about LT Spice, right? You can play with these things, because that was another comment I had was, this was a good example of when you're trying to understand a basic concept, and you can use LT Spice to help you get your head around it, because you can read textbook after textbook and chapter after chapter on these subjects, and it gets pretty dry. And sometimes it kind of helps to see a little bit of a practical experience. Of course, then you got to take it to the breadboard on your test bench, right?
And that's why I do everything now in LT Spice, because I like to test it, like to see what's going on, and I like to understand it. Because if it doesn't work, it means I've done something wrong, obviously, or I just don't understand something.
Yeah. Hassan, you got a comment?
Yeah. Can you guys hear me, first of all?
Yes.
Okay. About the voltage kickback, I thought of another analogy during the presentation. If you're blowing into a balloon, what happens at first when the balloon is expanding? You feel this, it's resisting, so you feel this pressure, extra pressure, right? And then when the balloon, if you keep blowing and then at some point the balloon starts contracting, you're going to feel the reverse. It's going to contract and push the air out, and you're going to feel less pressure.
Yeah, that's actually a great analogy, Hassan, because there's no flux. And so when you first put air into the balloon, you're starting the flux. But as you start increasing the flux, you start getting resistance coming back. So yeah, that's a very good analogy.
Mm-hmm. And it also explains how the flow of air is outward, but the pressure is back towards your lungs.
Yeah, no, that's a great analogy.
Okay.
The other thing I like, Dave, that you showed there was when you took the criteria from that professor and did it yourself in LT Spice to see the results. I thought that was pretty cool. I bet you thought you knew everything when that worked out for you.
Yeah, because you know what? I put the MOSFET in, and I did it, and I was going, what? 100 millivolts? What? WTF? What's going on here? And so I started scratching my head, and I started playing around, and I started putting transistors and different MOSFETs, and then all of a sudden I thought, hey, why not just put a switch? Because you look at anyone talks about a buck converter, the theory of it, they talk about it's just a switch you need. And I thought, okay, let me just put a switch in. I put the switch, all of a sudden it worked. It's like, woohoo!
Yeah.
So you're right. It's like, okay, yeah. I did something right.
I can move to the bench. And it was good to see you using the voltage control switch, because I stumbled across that on a presentation back a couple of months ago. And I thought, oh, that's a pretty cool concept to use that thing. And I kind of forgot about it until you just used it again on this one here. Any other comments or questions from anybody?
Was this useful? Did you guys did you get anything out of it, or was it just yeah we knew this, Dave? Shut up.
I think for me, Dave, there was a couple of concepts. Oh yeah, that's a good refresher, like you had mentioned earlier. But also for me, it was showing how to use, in this case, LT Spice in helping understand these different concepts. And of course, by doing that, I think you also start stumbling across other things. For example, well, you thought you knew how to use the FFT in Spice, but you didn't. So that could be a topic for another day. What the differences was there now that you know how to really use it. And of course, the other one that really helps out, and I've just started to explore it myself, is using the measure statement in LT Spice to help grab the information that you need instead of doing it the old manual way kind of thing. Start using the power of LT Spice to do the calculations. For me, I thought
that is the most powerful feature in LT Spice I've found, because what you could do with that, it's just incredible. Because you could do harmonic analysis, so you could look at total harmonic distortion. So you could look at it, design your amp, run it, and look at the harmonic output, and it gives you a number. It says you got 1% harmonic output. And so you don't have to go and do an FFT. So there's a whole bunch of things in there. It's just that measure, the whole measurement stuff, that's one of the most powerful features in LT Spice.
Might be interesting sometime down the road there to do some comparisons on the real bench with the FFT that you get out of Spice. I think, Kevin, you had your hand up.
Oh, yeah, no, it was just, you brought back a memory, Dave, because one of the first things I did on my very first job out of school, I was testing a DC motor. And of course, when I had to disconnect it, I forgot to turn the power off. So I was disconnecting the field. This was about 300 volts at a few amps. And as I pulled the wire away, I got this big arc like a Jacob's ladder. And I thought, oh, that's probably not good. So I put it back, and then I went and turned the power off. So yeah, you reminded me how powerful it. Yeah, I put it back thinking, oh, I better leave that disconnected because it doesn't seem to be going away, right? So anyway, yeah, you reminded me just how powerful an inductor really is.
And you survived.
And I survived to tell about it. Yeah, but now I remember to turn the power off when I disconnect.
Yeah, but now you're happy to survive it, but now it gives you nightmares just thinking about it.
Well, young and foolish, right?
Yeah. Michael, you had a comment?
Dave, could you post or somehow make the presentation available so we can look at it?
No, I'm kidding. No,
it's proprietary. Okay.
Of course I can. I always do, Michael. I will. Yeah, no problem.
I'd like, if you wouldn't mind, so I can get at it. Maybe put it on Dropbox or whatever, so I can get at it.
Sure. Yeah. No problem.
Great. I want to have a good look at it. Thanks.
I'm wondering if the presentation would be smaller in size if we converted it to the PDF. Save it as a PDF.
Yeah, usually. Yeah, I think so. Yeah,
and then maybe.
Certain people might want to take it and tweak it and do their own presentation or do their own thing. So that's why, like, I'll put it as a PowerPoint. Yeah, it's bigger, but if you want to go in and work things out, you can.
Another option could be and I think, let me take a look at the club website, because I think I got Peter Taylor to post something there. Maybe I'll take a look there, because maybe that might be a good spot to post these presentations. I know it was a conversation we had a long time ago, but we never really came up with a decision on where and what we wanted to do with it, right? I lost my train of thought there.
I'd suggest.
Sorry?
I'd suggest posting both, because not everybody has PowerPoint viewers, right?
Yeah, but PowerPoint viewer is free download.
Maybe PDF and PowerPoint.
I just like to go back and look at the presentation later.
Yeah, I started talking and I started talking.
I think it's Eric has a big echo happening here.
Yeah,
There.
I was sharing my screen. I started talking and I was on mute. I've got Peter, I've got Michael, I've got about 58 slides so far in this presentation.
Wow.
And it's going to grow. It's probably going to go up to like 70 or 80 slides. Because I keep
It's
adding.
certainly interesting stuff. This inductor stuff is stuff we learned in university and all that, but it's nice to sort of see it laid out and think about it from basic principles.
That was 30 years ago. I can't remember that crap.
No, I don't either. I don't remember last week, let alone 30 years ago. Very interesting, Dave.
Okay, any other comments on Dave's chat tonight? Any suggestions of other components that maybe Dave could do? Or Eric? Well, I can hardly what you saying then you're going into MOSFETs next. Well, that ought to be really interesting there. Now you're getting into something, Dave.
Yeah, and in the future, I'm going to do another presentation on load cells. And probably Kevin knows a lot about these because he uses these all the time. But it's how a load cell works and how you use a Wheatstone bridge. Because I've been building these to measure thrust of airplane motors and propellers. So I'll be doing another presentation sometime in the future about a Wheatstone bridge and load cells, stress gauges or strain gauges or whatever they're called. Because you'd use those, right, Kevin? In the machines, yeah, I'm sure.
Yeah, I use it to measure tension and webs or plastic webs or on wires or whatever.
Yeah, exactly.
Yeah, they're useful devices. Expensive, but useful.
I've seen them in textbooks and I've never seen one in real life. I have no idea what they look like.
Not much. It's a piece of aluminum with a hole on it, usually, or a hole in it, and then across the weak part of the hole, they glue a strain gauge. That's it.
Yeah, and the strain gauge, all it is, it's a trace. It's a film trace. It's a piece of film, and they've got a wire trace going back and forth, back and forth, back and forth, back and forth. And what happens when you bend it or you stretch it, the resistance in that film changes a very
ever so slightly, yes.
Right? And if you shrink it, again, the resistance in that little back and forth changes so small, and you need to amplify that change. And that tells you whether you're under tension or torsion or whatever, and how much the force is.
How do you connect that, Dave, to one of your plane, your model plane engines?
For measuring, taking a motor. So you take a motor and you put a propeller on it, right? And you want to know on a certain battery how much thrust is that motor going to produce, and is it going to have enough thrust to make the airplane fly?
Oh, so it's the thrust that is acting on that membrane is what you're measuring.
Yeah. So see, it's just like a scale. This is exactly like a scale, right? You put your weight on top of it, and it deflects. And this is exactly what's in a scale, right? And it deflects. You can see the thing deflect. It's more the 3D printing thing is deflecting, but yeah, it deflects, and that's measuring the thrust, the weight, the force.
And how would you do that with a rocket motor? Just off of the deflection plate?
Same thing. You just attach a rocket motor to it, and that's what NASA and those guys do. They take a rocket motor and have a big honker of a strain gauge, and they measure the thrust, right?
Another example of you combining a couple of different hobbies into one.
And that's what I love about home brewing stuff, right? Because it's all electronics, right?
Good stuff. Okay, any other comments, questions? Kevin.
I just I misspoke earlier. I must not have looked too well for the price on that one chip. It is at Mouser. You can get it. it's 57 weeks lead time, and it's $93 US, and they have 0 in stock.
Oh, good.
So in case anybody's tempted, don't worry, you can't buy any right now. There's supposed to be some coming in a few months, but
What if you can get a sample?
I don't know.
Not at $93.
I somehow I doubt it. Yeah. So,
You know.
anyway, yeah, they are available, but just not on. It's not on a whim that you're going to go get one.
Yeah. All I know is you can't get samples when you're using a .gmail address. Anyway, another problem to solve at another date, I guess. Okay, anything else on anybody's mind tonight? No, well, I'm packing off to Florida on Friday, so I'm going to be taking a laptop down. I think I mentioned before you can take me out of the shack, but you can't take it all out of me. I'm bringing some of it with me, so I'm going to work on some boards for my projects that I'm working on down there. So when I get back, I can put them right straight to the CNC machine.
Recording is on.
Has got me thinking again about making that ultimate audio filter, and then of course that brings up some of these other projects the other guys have done, the IQ, you know, although they're doing it what do they call it, binaural audio on receiver. Always wanted to build one of those circuits, and but I'm wondering, I know they all base it on doing the IQ, splitting it off of the RF, and then converting to the audio that way. And there's your IQ audio. But can you split the audio and like have the RF come in the one, then split the audio off and have the same effect? I don't know. Anybody have any ideas on that one? To me, it's the same thing, right?
So what was the question again?
With binaural receivers, they split the RF off to 90 degrees to get your IQ, and then each I and the Q each have their own audio amplifier, and then that goes to your headphones. Now, what I'm saying is, can you, instead of splitting off making the IQ from the RF, can you just do it from the audio side of things? In other words, convert to the audio, the baseband, and then split the baseband into.
Sure, you can.
That's an interesting question.
Yeah, you can. Like, it's just a mixer. You're just going to have to mix the audio with, what is it, mixing with a cos and a sine wave?
Yeah.
Right? So you're just 90 degrees out of phase.
Exactly. And where I'm going with this was, when we ever get around to getting this DCR project finally underway, then can you do the audio IQ after the fact? And you'd have your binaural receiver.
Yeah, you'd probably have to do some fancy filtering, because like you take your audio coming in, mix it with, say, a 100 kilohertz signal, right? Raise it up outside, right? And mix it with a 100 kilohertz sine and 100 kilohertz cos wave. Take that and then bring that back down, right? Into audio, and then feed it out.
Mm. And then the filtering, I can just once that's all done, I can hand it over to Wayne's project.
Anyway, in terms of projects, now that I've got a spectrum analyzer, I'm going to have to learn how to use it.
Well, yes.
I'm going to have to screw up my courage and actually try to measure an RF signal. I haven't done that yet.
And you didn't blow it up?
Let's not go there.
Sorry, couldn't resist.
Actually.
Lord, hey, Michael, I'm only saying that because I did blow mine up.
Well, let me tell you, at the same time I got the analyzer, I have a linear here, and I hadn't used it for a long time, years and years and years. So I set it up, and I was talking to a guy locally, and I turned around, and a couple of days later, I noticed that the analyzer, which had been plugged in, you know, the little light flashes, and the light wasn't flashing anymore. Turned out I couldn't turn it on. So I don't know what happened. I don't know where the RF got into it. Anyway, RCC replaced it. No charge. They mailed it and made me another one, so I returned it. But nothing connected to it. So it must have gone. Whatever happened to it, it must have gone in through the power cables. It's weird. I don't
It's a
know.
weird one. I wonder if it was just coincidence that something happened, but it's.
I don't know. I had plugged it in. I got the analyzer and turned it on so I could see, but I didn't have any connectors or anything, so I had to get connectors. So I just looked at it, and then I turned it off, and then I, turned the amp on. I had it around 600 watts, I think, roughly on 20 meters, and had a conversation with someone. Didn't notice for a couple of days, and then I turned and looked at the analyzer, which is just to the right here, and it was dead. So I called RCC in Vaughan, and I said that I just had it for 2 days and it died. And I said, what can you do? And can I get it fixed, or can I get a replacement, given it's only 2 days? And they sent me another one.
Yeah.
It was very generous of them.
Well, that's good.
It's a 3-year warranty, so I guess,
Well, it'd be interesting to keep, if you can keep in touch with them, to see if they will tell you, or if they find what's wrong with it. And if not, then Dave, when you're down in Dayton this year, you can ask our good friend Jason there about that situation.
Well, David, yeah, Peter and I talked about, writing an appropriately worded email to Jason saying, asking, are these things susceptible to this kind of thing, and sort of explain the setup and see what he says, rather than actually admitting that I did it.
It just seems
I don't know. Maybe it wasn't me. Maybe it just died. I don't know.
It just seems strange that you would have that much stray RF going in your shack that it would actually blow up a piece of equipment that's turned on. Kevin, you had a comment.
Yeah, I have this little thing here too, right? It's RF Explorer. It's like a little spectrum analyzer, cheap and dirty. Nothing like what you guys have. But in the manual, it actually says and you can see I don't listen to it, but I also don't run my HTs nearby it. But if you have a 5-watt HT nearby this without like a dummy load on the antenna inputs, they said it will damage the inputs. So
yeah, but
this is right in this manual.
But you see, it wasn't the inputs that died. It was the power supply, because I couldn't turn it on.
Yeah, no, in your case, yeah. But are the inputs susceptible? Yes, I believe they probably are. But
so I'm wondering, should I get some end connectors and short them out and put them on the front connectors on the tracking generator and the RF in?
It's probably a good idea. I suspect if you dig through the manual, it may have that recommendation. I don't know. I don't have one.
No, nothing. I didn't see anything.
Nothing
also,
in there, right?
Should I unplug it? Keep it unplugged all the time?
Well, if you listen to the Ham Radio Workbench one on coax and connectors and all that, they actually suggest that very thing, is having a piece of good coax on there and having some kind of attenuator kind of almost permanently wired in to help save your spectrum analyzer from, unwanted RF.
Well, that will certainly be an interesting question for either an email to Jason or Dave when you're down there. And Dave, you have a comment as well. Oh, by the way, Kevin, retire, then you can get the big boy spectrum analyzer. Dave, you had a question?
Yeah, no, Michael, keep in mind the radiation is 1/r². So, my rig is running, 100 watts, and I've got, 10 feet, 6 feet, 8 feet apart. So you've got 600 watts. So, and it's right beside each other. So that 1/r² term is really small. So
the amp is probably 3 feet from the analyzer.
Yeah.
But my FT1000 MP is probably 2 feet.
There you go.
1000 MP is 100 watts.
You've got any stray RF coming out of that sucker is going to make it across. And keep in mind, they're both electrically grounded, right?
Yeah.
So if you've got any RF in that third pin, it's going into the unit.
So I think I should, as a matter of routine, leave the analyzer unplugged.
Yeah, I turn my analyzer it's on a power bar, and that power bar is turned off, and I got my analyzer, my wave generator, and my oscilloscope on the same power bar, and it's turned off.
Now you guys are making me want to rewire my whole shack now.
Well, I wonder, since Dave was talking, I wonder if I should put the oscilloscope on something like that, do the same thing.
Yeah,
because
I turn my stuff off. I leave my stuff turned off.
Well,
good idea.
what's good for one is probably good for the other, and as you're working on to deal with one, it's probably no big deal to take care of any other piece of equipment you got going in there.
Yeah. Well, I got the linear, and I got the MP and the two pieces of test instrument. That's about all I got. But yeah.
And keep in mind your SA, your scope, all of that signalant gear, it's not powered off. It's never powered off because you got that thing blinking.
Oh yeah, I know, that's right. But I've never had a problem with the
So
scope, and the scope survived.
It's got current going in it. It's doing something, right?
Yeah,
You know, you got to take a look at a schematic for these things and just see what is powered up, because I can't believe they got the whole unit's not powered up. But
Yeah,
you're
but
right,
it's
part of
it's
it.
got to be turned on because you got something blinking. So it's got some circuitry in there blinking it and some voltage coming in to make it blink, right?
Well, it's like your TV. It's like your TV. You can turn your TV on remotely. That's exactly how it works. It's something's always on.
Well,
Anyway,
it was a cheap lesson, I guess, Michael.
yes, very, very fortunate that
And
they just took it back.
I think what we find here in this discussion here would also suit the VNAs and tiny SAs and PARC SNAs and all these kinds of things.
Oh yeah.
About it. Okay. All right. What else have we got? Anything else? Any comments from anybody on anything? Anything want to bring up?
Well, I would say thank you to Michael for finding that, hooking me up with Cross Border Express again.
Oh, did it work?
Oh, so far I haven't heard anything from them except they had a package waiting for me and it was going to be shipped and they took a MasterCard and it's no longer showing on their website. So I'm assuming good things are happening.
Either that or they split the country with your credit card.
Well, that could have easily happened, you know.
Yeah. Well, if you know, if you gave them the approval, you would. I presumably when you registered, you gave them the credit card number. I think you have to do that, don't you?
Well, you do it when I had to do it when I told them to ship it to me. It was kind of a weird. I am the shipper, so I have to go in and initiate the process and give them the card for payment and all. It was kind of strange, but that's all right. I mean, I know what they're doing now. I get what they're up to.
Yeah, it's really handy. I really like them. I think it's really good. I've used them a whole bunch of times. I have a friend, Bruce TMV down the road, that has one of these U.S. boxes that he had to go down there to get stuff. So he had to go into the States to pick it up. It cost him $3 a year or $6 a year or something. But this is much better.
I had one of those on Hill Island, but the minute I got it, COVID struck. I'd never been down, so never.
Well, I use it to. We built a lightning arrestor system for our club station for the antennas on the roof, and I went and got the parts from the guy in Utah that provides this stuff, and it was going to be like to ship a box that was, 20 by 20 inches and 6 inches deep, plus 20 arresters or something. Was going to cost over $250 to ship it, but it was like $15 or something, or $20 to get it from Utah to Niagara Falls, and then $15 or something to get it here, $20 perhaps. It was really much cheaper.
Yeah, I'm not sure I understand the overall politics of what's going on here, but this is a much more efficient and I think cheaper method than anything I've used before. So I appreciate that.
Oh, glad you like it. I really like it. It's good. And
Now
I've never had any problems either.
Now I have to go put shorting connectors on all of my equipment based on the horror story you just told me. So
yeah, thanks, Michael.
Yeah, I'm gonna spend the next 20 minutes trying to find a bunch of connectors and short them out and put them on
That's really good advice Dave has, to put those two pieces of equipment on a separate power bar and turn it on.
I have both a tiny SA and a nano VNA and all these things. And
well, it seems like when anybody buys an SA, it causes expense for somebody else. Dave blew up his SA, and that made me have to go out and buy all kinds of different attenuators.
And I did the same thing.
SA, and now I got to rewire all my 110 volt power bars and stuff like that to handle it. You know. So Kevin, when you get your essay, I can hardly wait to see what I have to buy after that.
Maybe we should both buy a bunch of MOVs.
He's not going to blow his up because he's going to listen to us and he'll know all the horror stories of the do's and don'ts.
Yeah,
And
hopefully I'll integrate all your lessons learned and not have any problems. Or I'll be special and find something else new.
That'd be special.
So Dave, you just turn the power off. You don't put shorting connectors on the front.
Nope. And like you saw back when I started building my shack, I had a ton of RF in the shack because I had that EMF meter and I was going around, and I had a ton of RF in the shack. And once I put my chokes on the coax outside and I was able to choke out the RF coming back, my lights no longer flicker. It's kind of cool. When I keyed down, my LED lights in the basement would flicker. It was really cool.
I never leave any connectors on the essay at all, because I always think that when you got the connector attached to it, you're forcing that pin apart, right? And if you left it in there, maybe that pin might relax a little bit. That's my theory anyway. So I don't leave any connectors in.
Maybe it's enough just to
that's
unplug
actually
it.
a good point, Peter. That's actually, it's
You mean the end connectors on the front?
Yeah, if you look at your end connector on the essay itself, it's like a little split, right?
Yeah, that's right.
So if you had the pin in there permanently, would it relax? Would it form to that and kind of loosen up a little bit? And we know how sensitive these things are. Anyways, you just look at your cable and it changes the reading.
You know who could give us some real good advice on this is Simon. Because if you think of Simon Shaw, he's got a lot of sensitive equipment. He's got a ton of stray RF, right? So he probably knows how to deal with this, right? Because he's got that shielded room.
His Faraday cage.
Yeah, it's Faraday cage. So he'd be someone good to speak to about this.
So
we should invite him to do a presentation. How to protect yourself. How to protect your gear.
I'll talk to him.
Mm-hmm.
Need to get him back out onto a meeting anyway. Okay.
By the way, Peter, speaking of getting people back, do you guys ever hear from Gord?
No, last time I talked to Gord was probably I was going to say a couple of years ago, but no, way before COVID hit. So probably about 4 years ago, I guess, maybe at least. And I asked him how things and what's happening and stuff like that. And he just said he was busy with evening shift and work. And
so he doesn't dabble anymore? Because I kind of miss having him around.
Yeah. I'm not too sure what's going on there per se, other than maybe he might come back one day. I think he came out to one homebrew meeting, and then that was basically the last touch I said. And I don't know if Frank or anybody else has talked to him at all. No. Maybe time to reach out to him again, I guess. Okay. Anything else?
You've talked to him more recently than I have.
Oh, is that right? Yeah.
Yeah.
And that's a long time ago. It could be a whole different kettle of fish now. Who knows what's going on?
Yeah, I got a question for Frank.
Yeah.
Frank, that painting in the background behind you, is that a painting?
No, that's a enhanced photograph, and it's of Stony Lake in the Kawartha area that I love and we've camped in. I did not take the picture. I happened to run across in a flea market north of Guelph, and I recognized the setting. So I talked to the fellow there, and he said, yes, he took that picture. In fact, he set it up a little bit because the boat was not at the dock. It was on the other side. So there was nobody around, and he moved the boat to the other side of the dock to make a better picture. And when he was finished, he put it back. And he has a very expensive color printer at home that prints these things out. and it's enhanced through one of the I don't know, photo software that you can get, and it came out just beautifully. So I bought the picture right away.
Because it almost looks like a painting. Because
It does. You definitely looks like a painting, but it's actually a photograph, and it's the enhancement that makes the changes in it.
It looks great. It looks great, Frank.
Love that, Mike.
I have to go, guys. I'll see you later.
Okay. All right. See you, Michael. All right, guys. It's, any other comments, questions? Okay, so I guess their next meeting will be March 2nd, and for the F mixer, and I guess we'll have a little bit of a change up on the order there. I think Dave is going to take the helm for us there. Eric is going to be away in some stupid place south, and I'm going to be in another stupid place south as well. But I'm hoping I'll be able to join in. I just got, when I get down there on Monday, I'll tell the family what my schedule is, and they can work around me. How do you like that theory?
Good luck with that.
So I promise I won't have shorts and my feet up by the pool when I check in.
Okay.
Okay.
Why not?
Of course I'm going.
Rub it in our face.
Of course I'm going. All right.
Great presentation, Dave. I really enjoyed it.
Enjoyed it. Look forward to the next one.
Good.
7-3, guys.
Nice.
Great, guys.
Good night, all.
Eric.
Yep, I saw. Yeah.
Yeah, we got to work on Peter.
Yeah.
You know
I
what?
see you're getting it worked in.
It's bad enough that I've made the decision I'm not going to go. I'm going to wait another year, but I don't need my so-called pals and buddies that are going to be rubbing it in and bugging me over this.
Hey, have you seen who's going, man? It's like you got Hans Summers, you got Farhan, you got all the movers and shakers going.
All-star.
Yeah.
Hey, what's the buildathon? I looked on Rex's site there and I didn't see anything referred to.
It's not going to work in any case. It doesn't matter. Does it matter? Because it's not going to work.
No, but they're advertising, you got to register for it.
I know.
You can't register for it.
Yeah.
I don't know. I was actually just talking to him earlier today, and I forgot to ask him, but I will next time I'm chatting with him. So
What happened to the buildathon from that tube kit that you guys signed up? Did that ever happen?
Got it.
Yeah.
I got it.
Yeah.
I got to build it.
they were all sent out, and there's been chatter on the QRP IO group. So yeah. I haven't heard too many success stories, but it's a Rex kit. So
Turn off your recorder.
oh yeah, right.
So did you guys build them then?
No.
Nope.
TBD.